In this lecture, we'll introduce one of the most fundamental concepts in calculus, namely the derivative function of a given function. And by the end of this lecture, we'll not only define the derivative function, but also demonstrate how to compute it for simple polynomial function. So let's dive right in. What is the definition of the derivative function? Often denoted as f prime of x or df over dx for a given function f of x. It is defined as the limit of this expression inside the square brackets called the difference quotient as h approaches 0. To understand this expression better, let's consider this graph of general function f of x. On this graph, we label 2 points, point P with coordinates x and f of x, and point Q with coordinates x plus h and f of x plus h. Now we'll draw a secant line that connects these 2 points P and Q. Why do we care about this secant line? Because its slope is going to give us crucial insight. As we know, the slope of a line is defined as the ratio of the change in y to the change in x. Now, using the coordinates of P and Q, the change in y, or delta y, is f of x plus h minus f of x. And the change in x, or delta x, is x plus h minus x, or simply h. Then the slope of the secant line becomes f of x plus h minus f of x divided by h. And this is exactly the expression for the difference quotient in the above definition. In other words, the difference quotient represents the slope of the secant line connecting the points P and Q. Finally, as the definition states, we now need to take the limit of this difference quotient as h approaches 0. And let's visualize what happens during this process. Given the secant line, shown here in gray, connecting the 2 points P and Q on the curve f of x. And as h becomes smaller and smaller, the 2 points on the curve P and Q move closer together. As you can see in this animation, the secant line begins to converge to the line tangent to the curve at x. This means as h approaches 0, the slopes of the secant line must also converge to the slope of the tangent line. So in a sense, the derivative f prime of x represents the slope of the tangent line to the function f at the point x. And this is the core idea of a derivative as the limit of the slopes of secant lines. So feel free to pause the video and take a moment to understand this very important concept. Now, how can we apply this definition to compute the derivative of a simple polynomial function? Let's work through an example together. Consider the following second degree polynomial function, f of x given by x squared. We will now use the definition of the derivative to show that its derivative function is 2x. First, if f of x is x squared, then f of x plus h is simply x plus h squared. Expanding this expression using the distributive property or foiling, we get f of x plus h as x squared plus 2xh plus h squared. Again, by definition, f prime of x is the limit as h approaches 0 of this difference quotient. Next, substituting f of x plus h with x squared plus 2xh plus h squared and f of x with x squared, we get the following expression. Now, after canceling x squared from the numerator, this becomes 2xh plus h squared divided by h. Let's note that here, both terms in the numerator can be divided by h. Then this simplifies further to 2x plus h. Finally, as h approaches 0, the h term vanishes, leaving us with f prime of x is 2x. And this is exactly what we wanted to show. And it wasn't too bad, was it? I hope this video helped you understand one of the most fundamental definitions in calculus, namely the definition of the derivative function. So if you enjoyed this lecture, be sure to like and subscribe to my channel for more useful videos.